All right, good evening, everyone. Today is Wednesday evening, the 20th of March. The paper that we are going to read is actually a slightly older paper, and it has been one of the milestone papers that led to a lot of downstream work. The title of this paper is LLAVA, Large Language and Vision Assistant. Visual instruction tuning. I would focus more on the title, visual instruction tuning, and see what it means. Now, this paper was followed by a subsequent paper, which is LLAVA 1.5. I believe there's also a 1.6 or something. But then there was also an adaptation of it, a LLAVA with RLHF, that is reinforcement learning with human feedback. That work was jointly done by pretty much the same people, and I think Berkeley was also involved in that. Then there was also LLAVA that was applied to the medical domain, LLAVA Med. So there has been a lot of downstream work that has been associated with this particular research paper. Now, this research paper is actually the pace at which our field is moving. It is a little bit older paper. The request for this came actually from our boot camp, which we are doing on Sunday. We were covering a few papers. We covered CLIP, BLIP, BLIP2. And in some sense, this represented a natural evolutionary step beyond BLIP2. And one of the things we'll see is how this compares. In the paper itself, we'll see how it compares, the results compare with respect to BLIP2. So before I continue, I would just like to summarize a little bit of the history or the prior work, if I may. So to do that, I'll get back to the writing pad. And before I do that, I suppose a demo is called for, but maybe we can do the demo at the very end after we have understood the paper. So for that, I'll now go back to my writing board as always and start from there. So forgive me for this quick, like if you are already familiar with CLIP, BLIP 2, then we can please humor me with this quick recap as I go through this. So to begin with, we know that when we have text, let's say that we have text that we can represent. Let me take a slightly smaller font. Yeah, a text. What we can do is you can use contrastive learning loss function. If you remember, what it means is that you take some text, let's say T. You take a similar text to it. Like, let's say that the cow jumped over the moon, and you take a sentence that's very similar to cow jumped over the moon. And then you take a random text. So our text, let me just put the word here, our text, something similar in meaning, or what you would say semantically similar. And then you would take some random text with the assumption that if you take a random text, it would be probably irrelevant to what the text is saying, completely out of context to this text. And then what you do is contrastive learning basically says that you sort of maximize, you project each of these texts into hidden vectors, hidden embedding vectors of the text. Let's say that this becomes hard. You use some mechanism, and in particular, you always use something like a BERT or an encoder transformer, encoder part of the transformer. And if you're not too much into it, just say there is a mechanism these days to convert text into vectors. So once you create the vector, contrastive loss or contrastive learning just means you minimize the distance between HT, the hidden vector for the text, and a similar text, and you maximize the distance between hidden text the texts, hidden vector, embedding, and these vectors are often called embedding vectors. Though, or more generally, these are the latent vectors, that that your encoder produces, and then you want to maximize the distance between a text and some random text. In other words, what you're trying to do is project it into a space at which things that mean the same thing or similar things are close to each other, HT and HS, whereas things that are random are far apart from those two. And when you do that, what you end up creating is a latent world, a latent or hidden. Latent obviously means hidden, a latent space of, in a way, meanings, or more specifically, you can say a semantic embedding. That's a word people often use. Semantic embedding you create into this space. Each point becomes, each sentence, and each piece of text, actually, more broadly, each piece of text becomes, goes and sits in this space at a point where the neighboring points are talking about the same thing, essentially, semantically are very, very similar. So that's a bit of a history that started this game. And now and obviously we now know these as sentence encoders. If you go to Hugging Face, you will see a zoo of this sentence encoder. And then there are benchmarks to see how good they are. MTEP is a benchmark that compares one, so there's a leaderboard and so on and so forth. So it's become an active area of work. And in fact, semantic search or AI search is literally a consequence of this embedding, right? The whole AI search evolution that you're seeing here. And that led to all these vector databases, etc., becoming rather big these days. They all are a consequence of this simple idea. Now, so that is the sentence encoder. What the clip was, just as a recap, a clip took a very interesting position. Before clip just asked this question, people have figured out a way to take an image, let's say an image of a cat, and they have figured a way out to convert it into, encode it into a vector. Once again, let me just call it a cat. There are multiple ways you can do it. You can do it using a CNN, convolutional network, neural net, for example, a ResNet. But these days, much more prevalent is to use something called a visual transformer. And just to give you an idea of what a visual transformer is, in case you haven't encountered it, it breaks up the picture into little patches, typically 16 by 16 pixel patches. And it says that what if we treat this entire picture as, in quotes, a visual sentence, where every single patch, 16 by 16 patch, corresponds to a word. And now you say, how can it correspond to a word? The way you do that is you take the 16 cross 16 pixel matrix, and then you multiply it by some projection matrix to linearize it. So for example, if I multiply it by a 16 cross 1 matrix, you will end up with a vector, right? And this vector would be pretty much a flattened version of this particular patch, right? So you can flatten it using a projection matrix. And this is a standard matrix multiplication, but think of a way that somehow you can convert this into a vector. And once it becomes a vector, then if you think about a transformer, an encoder of a transformer, what does it take? It takes word embeddings with, of course, the position embedding, but position embedding is implicit here. And then you feed it in, and what it will produce is lot of these hidden latents. And then one special latent that you take is the latent of the first token, the CLS token, and that you can consider as either the proxy or the representative vector for the whole, the entire image You could do that. Or some people in some alternative implementations, they just mean pull it. They just take the average over all the hidden, all the latents. So one or the other, one way or the other, you have a way to make an image into a vector. Now, the moment you make an image into a vector, and that is the VIT, which this clip uses, clip actually goes and says you can do it with VIT or with ResNet or whatever. But the moment you do that, the same VIT or the image encoder plus the same contrastive loss, what you can do is you can say, hey, given an image and given a caption associated with the image, suppose you have data like this, and how in the world can you get data in which you have image and caption? And how can you gather that at web scale? One easy way that the clip paper did it is they just went and scraped the web. Think of Common Crawl. And in HTML, for example, people write tags like this: img src is equal to blah, 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 some image. And then they put alt, which if dutifully, if people have been doing well, they would be putting description of the image. It's not always there. Actually, the data is very, very noisy because most of the time people forget to put alt. And many times, because people do search engine optimization, the text that they put are just keywords. It has nothing to do with that image. Right? So given all those defects or blemishes, nonetheless, the researchers behind CLIP managed to harvest a vast amount of sort of pairs, image and caption pairs. And then with the image and caption pairs, they basically said that what if we do this? We train a contrastive loss function that minimizes the distance between the hidden state of the image and the hidden state of the caption, the latent of the image and the encoding of the image and the caption. And that makes total sense because if you do that, now what happens is going back to our semantic embedding. Now, not only are texts sitting here as texts that mean the same thing, but also images. For example, this would be the cat jumped, and there may be a picture of a cat jumping. Right? These two things then come together. So what CLIP opens the door to is multimodal. The first breakthrough sort of multimodal, if nothing else, retrieval or search. Now you can search not just by text. So suppose you're searching for something, query word. You can convert the query into a query vector, H query, and then find its k nearest neighbor, find k nearest neighbors in the latent space. And those would be your search results, right? These neighbors would be your search results. So you now suddenly have multimodal search capability. And the capability is quite impressive if you have seen this. So moving forward, what people looked at CLIP and they felt that they would like to build upon the idea. So the next, in a way, there are many milestones and many papers came about. But the one paper, like there was an idea called Blip, and then Blip evolved to Blip 2. And in the past, we've covered that, but I'll just summarize what Blip 2 is because it will form a good background for this paper. What Blip 2 did is it said, okay, let's do one thing. Let's keep a encoder, like a clip-like encoder for images. So suppose you have a cat. Well, my cat hardly looks like a cat, but it is. And you get a image vector here. And what you do is you take a full-blown language transformer. They said that, see, to generate caption about this image, suppose you want to give it the generative task. What is this image? Describe it or generate a caption for it. What you could do is you could put a LLM as a decoder, and then you wire the two together with the ability that you could add some text input also. But what would happen is the text the hidden state of the text. I mean, there's a lot of things happening here, but I'll just put it this way: the text, the contrastive loss is still there. Image text contrastive loss is there. Image text matching loss is there, and of course the decoder loss is there. It means you expect a certain caption to come out. You happen to know the ground truth, but what is it? What is this machine producing? And that would be the decoder loss. So by training across three losses, the image text contrastive loss, which is the same as the clip loss, the image text matching loss, which is your standard sort of a binary cross entropy loss, and the decoder loss, three loss terms. What they found is that, and this is called the query transformer, just the glue, little bit of glue that that basically uses the image to ground everything that happens thereafter. It creates the input text embedding itself to be grounded in clip. So there's a bit of machinery here to deal with the internals, which I won't go into, but we'll stick to that. But the bottom line is that when you create an architecture like that, you take a clip model off the shelf, yeah, or image encoder model, you take a LLM off the shelf, you keep them frozen, you don't change that, and you just train a tiny little thing inside query former, which has been colloquially called just the Q former now. You train the Q former, and basically this thing works very well. Amongst its many benefits is that it produces a pretty good caption for images. So the query former has a property that it acts both as an encoder, as in, for example, search purposes, because if you don't give it a text and if you just produce the hidden representation, you could take this output and say, okay, I'm done. Here's a way for me to generate encoding for images. It does a very good job. It can also, and therefore it can be used for search, but it can also be used for decoder or generative tasks. The classic being captioning. So it became very popular for image captioning. And in the past, we have covered this, that the results are quite impressive. So that is sort of, let's take that as a background. And with that background, now ask, what is the contribution of this paper, LLAVA? This paper sort of builds upon the idea that just as you went from GPT, let's say GPT-3 to ChatGPT, if you remember, what was the gap? Like, what caused a typical, or more generally, an LLM to chatbot? Like, what makes a general purpose LLM, any LLM, behave in a conversational way with human beings? So if you were to ask that question, then you will be reminded that you have to do instruction tuning of this. Oh, 1 second, I noticed that. You have to do some, and the classic paper that you look at is the instruct GPT. And I'll just give the very basic idea. What it meant, instruct GPT did is, it took GPT and it basically said that instead of training GPT, which we have been doing, with just text and do the next word prediction, what is the next word that you're getting? What if you could write it in a very particular way? You could say question, answer, right? Question, answer, or rather question, input. Like, for example, it could be, what is the sum of the two numbers below? Sum of two numbers below, A, B. And then answer. Then what happens is, if you feed it like this, and these things, like a very structured text that you ask it to predict the next word of, if you do this, these are called instructions, or it's just a format of writing text as far as the machine is concerned. But because these machines have seen a lot of these hashtags or HTML tags and so forth, they pretty much know that these are boundaries, demarcators. And then what you do is, once you feed in enough of these, then you can just feed it a question, and you can let this ChatGPT and these things do completions. It will complete it with an answer. whatever is the answer, right? It knows that when I get a question, that I need to respond with an answer. So the classic example that is given in this context is that if you take an LLM and a normal LLM, which has not been instruct tuned, which has not been instruction tuned, the way that we are doing here, but where if you ask it, what is the capital of France? Now there are two possibilities. It can just say Paris, or it can just say respond with another question. What is the capital of Germany? Right? Now, both of these, as far as the LLM is concerned, both are equally likely. In fact, this answer is more likely because typically there are lots of quizzes sitting there on the internet, list of questions that, for example, in school, teachers ask students and so forth. So in that particular case, it would have produced this. But once you instruct tune it, what the instruct tuning does to fine tuning, to supervise fine tuning, SFT, fine tuning. And in that paper, they use the next stage, which is reinforcement learning with human feedback. I'll put the words there, reinforcement learning with human feedback. What it means is that you give it some label data and then you also go through a whole process of RLHF. Uh, this is a slightly bigger topic, but we'll just leave that there's a way to do it in such a way that it aligns with what human beings would expect the answer to be, right? In other words, it will pick this answer and not go to the choice B, right? That's called human alignment, human preference alignment. And the word means exactly what it says. You do that. And that's what makes a GPT, once you do fine-tuning, instruction fine-tuning, it becomes, for example, a chat GPT. Okay? Or with any LLM, once you do instruction fine-tuning, you can have a conversation with it. And of course, one of the easier ways that you could do, for example, today, just download Olama as a software, run it, and you ask it to pick up any one of the open source models, and it will happily do that, and you could be chatting with it. So all of those models that you are chatting with using a tool like Olama or any one of its variants is basically you're looking at instruction-tuned LLM. So that's the word. Now, with that as a background, these two things formed. And the question, so now that you can do that, you realize that there's tremendous benefit in instruction tuning an LLM in the word domain. That sets the context or the stage for the question that the authors of this paper, the researchers, asked. The question they asked is, well, that's really good. It's pretty impressive. You could take LLMs, which were the toys for researchers and engineers, a few 10,000, let's say, of those around the world. And you convert using instruction fine-tuning, you convert it into something that hundreds of millions of people around the world are using, like ChatGPT. Can we do something? Can we, in a way, smarten up the visual language domain also with some form of visual instruction tuning? And therefore, the core message of this paper, which we'll come to, is this particular sentence. It is saying that, hey, let us do what Instruct GPT did to text domain and apply it to the visual domain. Let's do visual instruction tuning. But how do we do that? That is the question. Now, to understand that, let us first read the abstract of this paper, which is quite a bit. It says, I will read only part of the abstract. Let's read that. Instruction tuning large language models using machine-generated instruction following data has been shown to improve zero-shot capabilities on new tasks, but the idea is less explored in the multimodal field. A lot is said in this. See, when you just go to a chat GPT, or to Gemini or to Cloud, and or your own Llama open source thing, and you ask it a question, most likely it has never seen that question before. And so it responds. That is called a zero shot. The fact that it can still answer that, it is a zero shot capability. Right? So these instruction tuned large language models, in fact, most of our forms of interaction in some sense are zero shot, utilizing its zero shot capability. And it answers our question. But this idea is less explored in the multimodal field. Now, they go on to say, we present the first attempt to use language-only GPT to generate multimodal language image instruction following data. So first thing they do, they say that, okay, suppose our goal is, we want to do, let's take an open source model. We'll take a Llama instruction tune model. Let's say that this or and its variants like Vicuna. We take that and we say that let us give it visual instruction tuning. Means we can give it images in a structured format, image, or tell it that this is what this image means, or this is what it is, and that this is what is the answer that you have to produce, right? If you could do that, but first of all, you would need data, right? So what they say is that they use a language-only GPT to generate that training data. So the first stage is, and we'll come to that, generate training data. Because see, here's the thing. We have on the web, for example, there are large websites that will give you image and caption data, right? But the image and caption data, image and caption pairs, image, caption pairs, they are not sufficient to train. They don't have the sense of an instruction. What you need is an image, a question about the image, isn't it? An instruction with some answers, etc. Something like this. And you would want the machine to follow this, to learn from this sequence, just as we saw a little while ago, this the instruct GPT did exactly that to convert a LLM into a chatting LLM or human aligned LLM. If you remember, what did we give? What was the instruction tuning part? Something like that, question and answer, right? So you need to somehow feed it instructions, question, answers, but along with images, because now we have images that form the context of it. And so this paper says, let us go somehow and do that. And one way to do that is you use a powerful model like GPT-4, which can only do text. The initial, well, obviously GPT-4's visual version has also come out now, but they are not using that. They're saying, let's use a powerful model to generate training data, instruct data, training, instruction data. That is the first goal. Because if we can do that, then comes the next part. By instruction tuning on such generated data, that now they create a model that they want to introduce LLAVA, large language and vision assistant, an end-to-end trained large multimodal model that connects a vision encoder and a LLM to for general purpose visual language understanding. Right now, if you know blip2, for example, you say, well, that was this is somewhat reminiscent of blip2, right? So what is different? If you remember, we just talked about blip2. Blip2 was they put in the blip2, you put a query former, Q former here between a image encoder. This is your image encoder and a LLM. You put a query former. What is the difference? The difference is just like LLMs you just trained it with text and ask it to find the next word, right? The standard way that you would pre-train a LLM. Whereas your goal now is not to do that. Your goal is to give it proper instructions. like inspired by the instruct GPT kind of thinking. Give it an image, give it a question, give it an answer. So those form the instructions. So it knows how to follow instructions. But how do you generate those instructions? By using a much larger model. So that is the point that they are trying to make. Now we'll see how it works out. To facilitate further research on visual instruction following, we construct two evaluation benchmarks, etc. So now there is something to do about benchmarks and many other things. And then they show, as always, people have to show that the results are quite impressive. And we will see that indeed the results are quite impressive. So I won't go into too much of the introduction. Let us go to the core of what they are giving to us. They're saying in this paper, we present visual instruction tuning. So now I hope the word visual instruction tuning feels very intuitive in view of our discussion. The first attempt to extend instruction tuning to the language image multimodal space to pave the way towards building a general purpose visual assistant. Right? Now, what do you mean by a visual assistant? You can give it an image and say, what is it? But not just what is it, what is unusual about it and things like that. And many things, as we will look at the results, it is actually quite astounding how well it does. In particular, our paper makes the following contribution. And remember, this is the first version. There has been a lot of subsequent work after that. Multimodal instruction following data. One key challenge is the lack of vision language instruction following data. We present a data reformation perspective and a pipeline to convert image text pairs into an appropriate instruction following format. So this is the first contribution. On the web, you have image and caption. From that, they produce basically a data which is image and let me just call it image and let's say instructions. Instructions in the instruct GPT or that sense. So obviously that is a necessary thing for them to train their own model, which is the second part of it. Large multimodal models, which is the crux of what they are driving at. We develop a large multimodal model. And this word, by the way, is sort of gaining traction, LMM, large multimodal models, by connecting OpenSec visual encoder of CLIP, so CLIP we just encountered, with a language decoder, Vicuna, and fine-tuning end-to-end on our generated instructional vision language data. Now, you realize that a language decoder like Vicuna, it's an open source model, and then what they are saying is we fine-tune end-to-end on our generated instruction visual language data. So that's the crux of what they're doing. Then they go on to say our empirical study validates the effectiveness of using generated data for LMM, instruction tuning, and suggests practical tips, etc. Then they also contribute a benchmark. And then very nice thing about this paper is they say the whole thing is open source. Go at it. The code base, the model checkpoints, the data, and they even give you a demo. This part, guys, it is really worth applauding from these researchers. Most of the time, researchers don't pay as much attention, even if they release the code to GitHub. Quite often, the code is hard to, it's using a very old version of the library or something like that. And the data will be missing, or something or the other will happen. And or sometimes they won't even give the code. They'll just say, okay, here's the model, here are the weights. So when you see a paper that says we are releasing everything, the data, the code base, the model checkpoints in the training, and even a demo that you can play with and see the effectiveness of, that is something really worth applauding in the research. So I like that. It's something worth going into. So I won't go into related works and so forth. So let's think, what is it that they're doing? And this picture is actually says a lot. So I'll blow it up and go over this a little slowly. It says GPT assisted visual instruction data. So first part, remember, was just the data generation, right? was data generation. So how do they generate the data? The community has witnessed a surge in the amount of public multimodal data, such as image-text pairs, ranging from CC and Leon. By the way, if you're not familiar with Leon, I would highly encourage you to do that. I use it a lot. I use the data a lot to train or to fine-tune things and things like that. However, when it comes to multimodal instruction tuning, following data, the available amount is limited. So they point out that it doesn't exist. So before we get to that, let's see what do they mean. They say for an image XV, suppose you have an image XV and its associated caption. Sometimes you can do this very naive thing. You can say, okay, I have this cat. Right, this cat. And what I could do is there's a caption, cat on the window sill. You could just say, you could create a pair like this. You could say the data, the one part is take the cat's embedding, the vector that you produce by encoding the cat, right? Then you could take the cat image encoding. You could say, you could encode a question. Let me just put a question here and basically say, what is this? And the answer that you expect to be produced, like this is the input in some sense, and the assistant's output, like the way the Instruct GPT works is that you say, okay, a question or in context, XV, let us say, and then here's a question. If you think naively, this is the question. And the question could be something very boilerplate. What is this? And the answer that the assistant has to give, or the chat machine has to give, assistant or answer, should be whatever the caption that you found on the web. Right? The
Asif,
caption.
I can't say this fully. You may want to zoom out a little bit.
Yeah, that is it. So what you're basically saying is, if this is the caption, then what you can do is you can make it the thing that the assistant has to produce. Right? Now, it's a very naive way of looking at it. What they are saying is that if you do this, you're just encoding the image and taking a boilerplate question, and then telling you're creating the most naive form of creating an instruction to train the LLM, and you're saying, hey, this should be the answer from the LLM. A cat sitting on the windowsill, right? But when you do that, it will lack diversity because all the questions are boilerplate and the answers are not conversational in nature. A cat sitting on a windowsill is more a caption rather than a conversation or a description. It doesn't quite serve the purpose. So you need to be a little bit richer than that, right? So that's the point they make when they say, though cheap to construct, this simple expanded version lacks diversity and in-depth reasoning in both the instruction and the response. In fact, there is no reasoning. We are saying a cat is sitting on the windowsill. So to mitigate this issue, we leverage language-only GPT as the strong teacher. So you take a big model, both accepts to create instruction following data involving visual content. So how do they do that? Specifically, in order to encode an image into its visual features, to prompt a text-only GPT, we use two types of symbolic representation. And here is the beautiful thing. You use the caption that came with it and the bounding boxes. Now, what are bounding boxes and where do they come from? Bounding boxes, so when you look at this image, let's zoom into this image. Do you see these rectangles here around objects? Each bounding box captures some object that you recognize. This is basically image segmentation. Typical task of image segmentation. Right? So, for example, you can look at YOLO, right? YOLO, etc., etc. They will help you do that. These tools have been pretty well established. They'll help you do that. And so what they will tell you is things like this. Do you notice a person is there in this bounding box? So typically bounding boxes are given when you're given a rectangle. You give the coordinate of this point and this point, the xy here and the x prime, y prime here. Are we together? The top left and the bottom right, or one way or the other, right? So which is what you see here. That's why you see 4 numbers, not 8. You don't give the coordinates of each of the corners. You just give the coordinates of 2 diagonally opposite corners, and that's enough. Likewise for backpack, you do that for suitcase, etc., etc. So now already you know that a lot more is happening here, isn't it? You are giving the caption. You are also giving the bounding boxes. Now, suppose this information you give to a ChatGPT-like model or a GPT-4 model, or what will happen? It will begin to correlate, or it will begin to contextualize the caption written here in view of these objects that have been detected, isn't it? So it will be much better informed. It will know exactly how many people there are, how many suitcases there are, what is the location of the people in the suitcase. And so what you do is you use the GPT-4 to produce, and what they did is they played around with GPT-4 and ChatGPT, and they found that GPT-4 consistently outperforms. So they stuck with GPT-4, right? And they said that produce 3 kinds of response. One is the question answer kind of response. So one is, what is a good question that you can produce out of this image? So one question is, what type of vehicle is featured in this image? Right? Do you notice that it's a little bit more specific than saying, what's there in the image? It knows it's more specific. It's about vehicle. And the answer is, the image features a black sports SUV. Now, that is a very, very specific instruction that you can train a downstream model with. Likewise, you can say, okay, another kind of response you give is a detailed description. Now, this is what, if you notice that the large language models excel at, if you give it only, so remember, the large language model is not given the image. You can't give it the image, right? GPT-4, you can't give the image, or at least unless you use GPT-4 vision, but they didn't use that. They just gave this and this. These are the 2 things, the context, the bounding boxes and the caption. That's all, not the image. Image is shown here only as a reference. And then they say, okay, produce another type of response, the detailed description. So then it goes on to say, this image is an underground parking area with a black SUV parked. There are 3 people in the scene with 1 person standing here, another in the middle. Yeah. So how did it find that out? That thing where each person is sitting and how many people there are is not there in the caption, but it is there in the other information, namely the bounding boxes. And it inferred that. So you can already see that it can augment synthesize these 2, the caption and the bounding boxes, to come up with a better narrative, isn't it? So, and it did that. They're all working together. And then the third type of question that you create, response that you create out of the system, is a complex reasoning problem. You say that, okay, create a question that's a little bit, that is about reasoning. So what challenges do these people face? And if you notice, obviously now GPT-4 and these things can do this task very well. They will think about it and they'll come back with something. In the image, a group of people are standing, and it seems that the problem they are having is, how do you pack so much stuff into that SUV? I suppose that's a problem all of us families face anytime we go out on a vacation. Okay? So it does a pretty good job. So now what happens? What can we do? So now we have a this is our data generation. Given just this much, given this much, you can now use, the first part was generate a lot of instructions like this. Now that we have these instructions, what can we do now? That brings us to the second part. That is the visual instruction tuning. And this is the heart of it, what this paper is saying. So I'll zoom out a little bit and I'll say, so let us think through. This is a visual encoder, think clip. What will the clip do? So suppose I take the clip, I'll represent it like that, clip. let's say a visual encoder, doesn't matter. If you give it an image, a cat, then it is going to do that, and it is going to produce a hidden representation, a cat vector, isn't it? An encoding vector of the cat. But there is a problem. Then at the same time, you can take the text, whatever the language instruction is. But at this moment, I'll just vaguely use the word text, instruction. Instruction will, of course, be text. I can take it into text encoder, and I can convert it into a vector also, right? So now I have two vectors. There is now one problem. When you go from here, so the main problem that you have is this. Actually, I should take that back. What it does is it produces in the vocabulary of these people, it produces a vector ZV. They deliberately say that a clip may produce its own size vector. Let's say I'll just take a random number, 300 dimensional vector. But you're going to feed it into an LLM, a decoder, LLM decoder, right? LLM is here. If you're going to feed it into a large language model, which they represent as F5 here, if you're going to feed in, you remember that you need to feed it vectors. The sizes must match. Every LLM takes data of a certain size. So in between, you'll have to bring in a projection vector to convert it to the right size. It's common sense, right? So suppose I produce something like this, but this thing, suppose this is 300 dim, but the LLM says that, no, wait a minute, I will take something that is 1000 dim. I'm taking an example. So what will you have to do? You'll have to do a conversion of this to what this LLM is willing to take. And therefore, you will have to bring in a projection matrix, some linear transformation matrix, just a standard matrix that you'll have to bring in. So that explains the projection matrix here. You need to bring in. And when you do that, then what happens is that the projection matrix now aligns both of these things to, to what the LLM expects. Right? So very simple idea. So now, if you look at that, for an input image, we consider the pre-trained clip, and they happen to use this clip, VITL14, which provides the visual features. So this is it. So now, what are they saying? You do this, you get this. The grid features before and after the last transformation layers are considered in our experiments. So with small details, we consider a simple linear layer to connect image features into the word embedding space, because LLMs, they need word embeddings, right? Word embeddings of certain dimensions, let's say 1000 or 512 or whatever dimension that they want. Specifically, we apply a trainable projection matrix. So they're saying the weights, the values of the projection matrix are trainable. What does trainable means? At some stage during learning, let it pick it up through backpropagation, right? Backpropagation of the gradient, it will pick it up to convert the ZV into language embedding tokens, HV, which have the same dimensionality as the word embeddings in the language. So this is easy. Thus, we have a sequence of visual tokens. Note that our simple projection scheme, it is very lightweight. And so one of the things they say that, see, we used a very simple idea. We could have gone fancy. For example, if you're familiar with the BLIP2 architecture, which we talked about just a little while ago. Remember, you could use all sorts of contrastive loss and the whole architecture of BLIP2 and a Q-former, and you could have done image grounding and all of that fancy stuff. But they're saying, let's leave that for future work. We are just using a simple matrix, plain and simple. Now comes the training part. All that is fine, but what is your instruction? It still begs the question, what is your XQ? Right? What is your instruction? So the instruction part they talk about. What they say is that given an image, we generate a multi-turn conversation. So just like that, this question, its answer, the next question, its answer, so on and so forth. So T turns, total number of turns you organize. So what is the turn? Turn is between the question and the the machine's answer, assistant answer. human assistant, right? So you're training now the machine to study this role playing, that the human asks this, assistant asks this. Observe this. And by the way, you are the assistant. You're going to be the assistant going forward after you're fully trained. That's the basic idea. So we organize them as a sequence by treating all answers as the assistant response, all answers, like for example, these answers as the, where are the answers? These answers as the assistant response, and the questions are the human part. That is it. And again, the instruction part therefore becomes straightforward. You just take this. Now, what does it look like specifically for a sequence of length L? Now, this is like a bit of a mathematical reasoning. I'll just explain what it is saying. Oh, what just happened? I screwed up. I jumped all over the place. Where did I jump off? 1 second. I apologize for this. If you're feeling dizzy because I'm jumping around, I apologize. So let's look at this. See, this is, you're saying conditional on this image. What is XV? Image encoding. Conditional on this instruction, whatever instruction you have, this instruction, you're saying, what is the probability of the answer? What is the answer? You know what the answer is. So what do you want to do? You want to maximize this probability, isn't it? You want to train the model in such a way that the right answer pops up given this image and this instruction, in case you hide the answer. And that would be because you're giving it multi-turn. What are you doing? You're giving it one question and answer, one question and answer, question and answer, right? A human assistant format. So it is the same as the product of doing it step by step, the T turns, right? If you have a sequence of length L, you say, first question, maximize this probability, then the next one and the next one and the next one. Then only can you maximize the overall probability of the right answer, right? All the right answers. So that is basically, people tend to write that because it's a formal way of saying things in machine learning. But what it is saying is obvious. It's basically saying, let's go turn the dials on the machine in such a way that the answers are what we want it to be, much more likely to be what we want it to be. And as you can see, this is the system, some system, but basically human assistant, interleave it. Right? You do that. And so when you do that, the way they train, it is in 2 stages. It's interesting that they train it in 2 stages. What they are saying is, going back to the image, well, I'll blow up this image. See, what are the 3 things that can be trained? What are the 3 animals in the zoo? There is the visual encoder, the clip. There is the projection matrix W, and there is the LLM itself, the language model itself. Isn't it? Theoretically, they are all made up of weights and biases. So theoretically, all of them could be trainable. But what they do is, they go about it systematically. First thing is, they never touch the visual encoder at all. They keep the visual encoder as frozen, right? So visual encoder therefore goes out of bounds from the training process. In the first phase, even the LLM is out of bounds. So if I can't train the visual encoder and I can't train the LLM, what is the only thing that I can train now? Just the weights, the simple weight matrix. So they say that we will, in first phase, we will just train the weight matrix. Right? This is your stage 1. You just do this to train the trainable parameters, this one. You train the weight. Now, why would that be a good idea? Because that weight matrix learns how to align the image encoding to the instruction encoding, isn't it? And let us first learn to do that simple task efficiently. But once it is learned, then in the second part, which will be the real fine-tuning end-to-end task, this is where you now open the weights of the LLM also to be fine-tuned. So you have Vicuna, you just open out its weights and say, all right, now let's go at it. W is learned. It also can change a little bit if needed to. it has reached a pretty good state, alignment, but let it also be trainable. But more importantly, let's go fine tune the LLM, right? Now you say, why do I need to fine tune the LLM? Because, well, LLMs have been initially only trained on text. Now you're giving it a lot of visual information, right? All these things that you have created, but as text, because you have made it as question, answer, instruct. Image encoding, so image grounding in some sense, and there's instructions. And so if you think about it and you recall your Instruct GPT paper, there is a very close analogy to what they are trying to do. They're trying to follow a similar path. The goal was to create instruction and use the instruction to fine tune, except that this instruction is derived from visual information. That's why they call it visual instruction tuning, right? So when you look at the experiments, it is indeed very remarkable. So I'll show you this picture, which is quite improbable. I don't know whether it was just staged or how this picture came about, but somebody in his infinite wisdom thought that the best place to iron clothes would be hanging off the back of a taxi, right? So, and he's busy doing that. So obviously, this sort of things are created, I suppose, for academic purposes. What is unusual? You ask this, the user can now ask this question. So you notice that it responds very nicely. It can answer questions. What is unusual about this image? Now, you're not saying, what is this image? Observe that it's a very different level of question that you can answer. Right? You are saying, what is unusual about this image? And it says the unusual aspect of this image is a man ironing clothes on the back of a minivan or van. Right? This is not a typical place to perform this activity, as one would usually iron clothes in a more stationary and safe location, such as a home, using a regular ironing board. The scene depicted in the image is peculiar as it involves a makeshift ironing setup on a vehicle, which can be both unsafe and unconventional. Additionally, it's not clear how the man is able to maintain balance and stability while ironing clothes in such an unstable environment. So when you think about it, do you realize that this is a long journey from just clip or something like that, isn't it? Now, captioning or even with clip, this is really very detailed understanding, visual language understanding here going on. Right? And so this work did get a lot of notice for that reason. And then you can say, you can ask it, what is happening in the scene? And then it will describe the scene. And it will also say, it's the image depicts a man standing on top of a yellow SUV around, etc., right? What is unusual about this image? Ironing clothes. What is unusual about this? Now, when you compare it to what other things produce, let's look at what GPT-4 produced. By the way, you use GPT-4 as the teacher to generate the instructions. And then you train this. In effect, LLAVA was the student that you trained, but obviously with additional information, the image, the bounding box, and so forth. And do you see, would you agree that it seems to the teacher, the student seems to outshine the teacher now, right? What is unusual? The unusual thing about this ironing clothes, blah, blah, blah. Relative to that, look at the answer that LLAVA gave. So I'll just give you the same question. Look at the difference between LLAVA and GPT-4, right? And in contrast, I said that in the natural progression of things, in a way, the predecessor I would call blip 2, you notice that when you look at the answer from blip 2, a man is sitting on the back of a yellow cab. It is actually factually incorrect. It's not sitting. And when it comes to Flamingo, by the way, Flamingo, as if you guys will remember, was a major milestone in its own right with images. And it turns out Flamingo didn't do quite well. The man is drying his clothes on the hood of his car. Completely wrong, isn't it? So clearly, LLAVA seems to be doing substantively better. And that's the reason it got a lot of attention, actually. And there's so many interesting examples. So, for example, you can use LLAVA to annotate. And if you look at some of the annotations, they're pretty detailed and complicated. You can give it a picture like this. and it will keep coming up with answers. Then there's a science QA, it is able to handle that. Well, they have the conclusion and so on and so forth, but I suppose the conclusion is it's a foregone conclusion. This is very good work, right? So, and it did have a lot of impact. So I will skip over some of the things for you to do, but look at what it goes on to say. This one is quite interesting. Visual input example, chicken nuggets map. So somebody took chicken nuggets and created a map out of it. So the caption was, sometimes I just look at pictures of the earth from space and I marvel at how beautiful it is. Right. Now, the user was given this question, user, can you explain this meme in detail? Right. So this meme being this combination. And so it says the meme is the image. In the image is a creative and humorous take on food with a focus on chicken nuggets as the center of the universe. The meme begins with the phrase, sometimes I just look at the picture of the earth from space and I marvel at how beautiful it is. The main image features a tray of cooked chicken nuggets with the chicken pieces positioned to resemble the continents and islands on a world map. The meme playfully suggests that the chicken nuggets represent the earth and the various locations depicted in the photo are actually chicken nuggets versions of different places. The punchline of the meme appears in smaller text at the bottom, reading, I mean, it's not the real earth, but how beautiful it is, all is. This light-hearted and entertaining meme combines food and humor, using the image of chicken nuggets to create a funny and imaginative representation of the world. Right? So, I suppose quite remarkable if you look at this, I mean, in case you have seen, relatively, when you ask GPT-4, it has a much brief answer. This meme is a joke that combines two unrelated things, picture of the earth from space and chicken nuggets. The text of the meme suggests that the image below is a beautiful picture of the earth from space. However, the image is actually of chicken nuggets arranged to vaguely resemble the map of the world. The humor in this meme comes from the unexpected juxtaposition of the text and the image. The text sets up an expectation of majestic image of the earth, but the image is actually something mundane and silly. And Blip 2 and Open Flamingo don't quite do well at all. Blip 2 says, sometimes I just look at pictures of the earth from space and marvel how beautiful it is. It simply missed the joke. Open Flamingo goes even further. It says, it's a picture of a chicken nugget on the International Space Station. Right? So clearly you can see that this thing does quite well, actually. And this is very interesting. You give it a picture. And by the way, I found this to be quite interesting that you can do that. You give it a picture, my joke website, and you say, funny joke, put a funny joke and a push to reveal punchline. And then you give it now the instruction, the user says, turn this mock-up into an interactive website using HTML and JavaScript, replace the joke with a real joke. And this part, I hope, will blow you away. Just this open source model, which has just been trained with this very simple mechanism, now comes up with this complete code. And this is how this website behaves. My joke website, welcome to my joke website. Push the button to reveal the punchline. And when you do that, the punchline is, why was the math book sad? Because it had too many problems. Right? So guys, we can go on as the illustrations are one remarkable illustration after another. And I invite you to entertain yourself with these and see how wonderful it is. What are the meals that I can cook from these? Look at the visual language understanding here. You're looking at a picture. You're not saying, what do I have, or do I have strawberries? You're asking a deeper question, a reasoning question. Right? You're saying, what are the meals that I can cook with this? And then it goes on into telling you what are all the things that you can cook. I would like to do the fruit salad. Show me the recipe. And then it will only pick things that you have here in your fridge and do that for you. And then you can say, what are the things I should be cautious of about when I visit here? It's a lake. right, with a walkway, with a pier. So when visiting this peaceful blah, 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 there can be storms, there can be all sorts of things. Compose an engaging travel blog post about my trip to this place, highlighting the beautiful sceneries, joyful experience, and include possible anecdotes. So look at this. So for this, guys, just pay attention to this. You're not telling it which place, you're just giving it a picture, right? And say, now write a travel blog, and very helpfully, it writes you a lovely travel blog, right? So now, last week or this week itself, I think we did this iconic picture from the Titanic. What is the ending of this movie? If you remember, Blip was rather laconic. It said they die, right? So this is a little bit, you would agree, a huge improvement over this. In this image, a young woman, blah, blah, blah. The ending of the movie is known for its emotional and heartfelt scenes and so on and so forth. Right? And it's pretty detailed. And then you can ask, do you know who drew this picture? And it will give you practically the history of this. And then you give it a different picture. You give this picture, right? And then you say, do you know who drew this picture? And then it will say the painting depicts a dog in a humorous situation where it appears to be wearing a woman's dress and standing in front of a landscape. Although the artist of the picture is not explicitly identified, it could be a reference to the famous artist Da Vinci, and known for his artist and Mona Lisa. The painting is likely a creative and comical take on the traditional style and blah, blah, blah. So do you realize that this takes visual language understanding to quite a new milestone when you look at that? And you can go on and on, about it. So, for example, this one could be easy. Maybe even a Blip, one of the older things, could answer that. What is the name of the man in the photo? And it would say Elon Musk. But what about this thing? Now, what is the name of the man in the photo? And it still says the same thing, right? So it says that it has a very good grasp of the visual information in the picture, right? You're making so and so on and so forth. There are lots of things that it goes into. I won't go into, but I would encourage you to do that. But one of the things you could do is, and we should do that now. Now that we have done that, they have, as they promised in the paper, they have a website where you can play and demo on your own. So I would end by saying, let's go here to the GitHub. You notice, guys, that this is the GitHub of this paper, and all the subsidiaries. There's LLAVA 1.5 and so on and so forth. You can get the model, you can get the code, you can get the data set on which it was trained. And if that is not enough, they have literally put the demo here for you. So now LLAVA is in 1.6. More things have happened. Obviously, I didn't cover this paper, which is an improvement over LLAVA. This improved baseline for visual instruction tuning. This paper. We won't have time for that, but the demo. And here it is, the demo. And you can put an image of your choice. Right? Maybe we can go Google an image. Let's go and Google some funny image. Weird picture of just a weird picture. Let's see what comes up. Image. Well, this looks not so good. Let's say unbelievable, hard to improbable picture. And improbable picture. Let's try our luck with this. What is improbable? Well, nothing seems too improbable in the pictures here. So I'll let you guys try out on your own. But let's just play with the examples that are there, that are referred to in the, what is this? Oh, by the way, this also allows you to use your camera. All right. What can we do with this picture? I don't know whether it took the picture or not. And oh, okay, I'm not able to figure out what to do with this and how to take it. But I suppose there's some way to take a picture from your camera and upload it here. Now, this is the thing that we saw in the paper, examples. And the interesting thing is you can play with the parameters, the temperature. Now, you know that these are all the parameters of the LLM. The language models, the decoders have these parameters like temperature, top P, max output token. Why? Because at the last layer, there's a softmax. Softmax is controlled by a temperature parameter, and top P means what is how much probability it has to accumulate up to in the top most likely things, and so on and so forth. And what's the maximum output token that you want? And then what is unusual about this picture? Maybe you can change it to let's try that. The yellow curve, the taxi is likely due to the city's regulation of branding. So on and so forth. So you can think of a more interesting, I suppose, examples and play with it. So that ends our paper reading. Let's have some questions if anybody has. Any questions, folks, before I stop the recording? No questions.
Asif, one question, Asif.
Go ahead.
For that, this first phase of their work, they use the ChatGPT or GPT-4. So ChatGPT, how can they use with the images? Because ChatGPT is only for the text, right?
No, the whole point is they don't give the text. So this was the point I was making. What they did is, let's go back to the image, to the part of the paper where we are.
They give text and boundaries.
Yeah, they just give the caption and exactly, they give the caption and look at this. So when you look at this, what are they giving? Context 1 and context 2. First is the caption and the bounding boxes. They actually don't give it the image. You can't. Right? You just give it the caption and the bounding boxes. How do you compute the bounding boxes of an image? Just pass it through something, segmentation thing, YOLO, etc.
Right? But with this bounding boxes, the numbers doesn't make any sense to the ChatGPT, correct? Because it doesn't have any context for that one.
Large language models are actually pretty good at it. They have figured out these things quite well. Remember, they have read. Whenever you think of these language models these days, given the amount of knowledge that they have absorbed, you can think of a guy with 1,000 PhDs. So certainly it has read enough geometry books and enough image segmentation books to know what bounding boxes are.
Right, but these coordinates, how it knows that, okay, these coordinates are related to this picture.
Oh, no, you don't give it the picture at all.
Yeah, that's what I'm saying. So how yeah.
Because in the system at the beginning, you give it a preface. You're saying, here is the caption. Here are the bounding boxes that are associated with with an image. You just give it some instructions. You say,
oh, okay, I see. Okay.
That picture is described by this caption, and here for the objects that are found in the picture, here are the bounding boxes.
Okay, got it. So it has the textual context for those bounding boxes in the captions. Okay.